You know, in our relentless search for clean, reliable energy, the biggest breakthroughs aren't always the newest or the flashiest. Today, we're going to talk about a true workhorse of the energy world, a foundational technology that's been quietly powering critical infrastructure for decades. It's called the Phosphoric Acid Fuel Cell, or PAFC for short. So here's the game plan for this explainer. We're going to start with why this thing was even created. Then, we'll peek inside the box to see how it works its magic. We'll look at the really elegant chemistry behind it, the pros and cons of its design, and we'll finish up by talking about its impressive, long-lasting legacy. So, what problem was the PAFC built to solve in the first place? Well, imagine you're running a hospital, or maybe a hotel, or a massive data center. You absolutely need clean, dependable electricity, 24/7. Relying only on the main power grid can be risky. That is the exact challenge the PAFC was designed to meet, giving you power right where you need it, whenever you need it. And this isn't some far-off, futuristic idea. The PAFC has a really distinguished history. It was actually the very first type of fuel cell to be successfully commercialized. It made that huge leap from the lab right into the real world, powering our most critical buildings. And the scale of its development is seriously impressive. To date, more than 85 megawatts of these PAFC demonstrators have been built and tested all around the globe. Now, to put that into perspective, that's enough juice to power tens of thousands of homes. So this is not some niche experiment. It's a proven and widely deployed technology. All right, now for the fun part. Let's pop the hood and look inside this power box. How does it actually turn fuel into electricity so cleanly and efficiently? Well, it all comes down to three key components. Okay, what you're seeing here is pretty much the heart of the fuel cell. On one side, you've got the anode, that's the negative electrode. On the other side is the cathode, the positive one, and then sandwiched right between them is the secret sauce, the electrolyte, which in this case is phosphoric acid. So here's how it all works. Hydrogen fuel comes in at the anode. A platinum catalyst there splits it into positive protons and negative electrons. Now, the phosphoric acid electrolyte, it acts like a really picky toll booth. It only lets the protons pass through. This forces the electrons to take the long way around through an external circuit. And that powerful, directed flow of electrons, yep, that is electricity. Then, over on the other side, at the cathode, those protons and electrons meet up with oxygen from the air, and their big reunion creates the only major byproduct, simple, clean water. Now let's take a quick look at the simple but really powerful chemical reactions that make this whole elegant dance possible. It all gets started at the anode. So first up, at the anode, this little equation shows exactly what we just described. One molecule of hydrogen gas, H2, gets split into two hydrogen protons, H+, and two free electrons, E-. This is the step that basically unleashes all that electrical energy. Meanwhile, over at the cathode, the second act is going down. Here, oxygen from the air combines with the protons that went through our electrolyte toll booth and the electrons that took the scenic route. They all come together to form H2O, just plain old water. And when you put it all together, the whole process is just beautifully simple. Hydrogen and oxygen go in, and you get two things out: useful electricity and clean water. That's it. No combustion, no nasty emissions. It's an incredibly elegant way to generate power. Of course, no technology is perfect, right? And the PAFC is a great example of those engineering trade-offs. One of its most defining features is its high operating temperature. And that heat, well, it's a real double-edged sword. On one hand, running hot, we're talking around 200 degrees Celsius, is great for performance. It boosts efficiency and makes a cell more tolerant to pesky fuel impurities like carbon monoxide. But on the flip side, that same heat puts a ton of stress on the internal components over time. It can accelerate corrosion and means you need to use more expensive, durable materials to build it. This brings up a really important question for pretty much any fuel cell. We know the high temperature helps a bit, but what happens when the hydrogen fuel has other stuff mixed in? This chart does a fantastic job of showing a problem called catalyst poisoning. Just look at those lines on the graph. Each one shows how the cell's voltage, basically its electrical power, plummets as you add more carbon monoxide to the fuel. See how those lines get steeper? That means even a tiny bit of CO forces the cell to work way harder. What's happening is the CO molecules are basically clogging up the platinum catalyst, stopping it from doing its job of splitting the hydrogen. And for other contaminants, the tolerance is even lower. For sulfur compounds like hydrogen sulfide, The fuel has to be incredibly pure. We're talking less than 50 parts per million before you start risking rapid cell failure. It really highlights just how critical it is to have clean fuel to keep these powerhouses running smoothly. But, despite these challenges, the PAFC has this incredible story of success. And it's all driven by decades of brilliant material science and engineering. So let's take a look at how it evolved. Back in the mid-1960s, these cells were just packed with expensive platinum, a whopping 9 milligrams per square centimeter, and they used exotic materials like gold-plated tantalum. But the real game changer came about a decade later with the use of carbon and graphite. This allowed engineers to slash the amount of platinum needed by over 90%, down to just half a milligram. That was the key to making this technology commercially viable. This quote really says it all. The shift to graphite was pretty much the single most important breakthrough. It gave them the perfect mix of electronic conductivity, corrosion resistance, and importantly, low cost. Without it, the PAFC would probably have just stayed a curiosity in a lab somewhere. And the results of all this innovation, a technology that's proven to be incredibly durable. Today's commercial PAFCs have demonstrated a component life that exceeds 40,000 hours. Let that sink in. That's over 4.5 years of continuous, nonstop operation. In a world that depends on constant power, that level of reliability isn't just impressive, it's absolutely essential. So, let's do a quick recap of what we've covered. Phosphoric acid fuel cells are not some future promise. They are a mature, proven technology that's out in the world right now. They provide exceptionally reliable power right where it's needed, with just water as the main byproduct. We learned their high operating temperature is both a strength and a weakness. And finally, decades of innovation, especially with materials like graphite, have turned them into the cost-effective 40,000-hour workhorses they are today. And that brings us to our final thought. We have this quiet, clean, and incredibly reliable powerhouse that's been trusted for decades. So as we look to the future, with the massive energy demands of things like data centers or the need for clean power in marine shipping, you really have to ask yourself, where else could this proven technology be the perfect solution?